Today we start a very important topic, hybridization. So, our topic for today, hybridization. When we consider the valence bond theory with our previous knowledge, considering the elements beryllium, boron, carbon having atomic numbers 4, 5 and 6, seeing the respective configurations 1s2, 2s2 for beryllium, 1s2, 2s2, 2p1 for boron, 1s2, 2s2 and 2p2 for carbon. We observe that beryllium, the 2s subshell is completely filled having 2 electrons. In case of boron, 2s is completely filled, the 2p subshell has got only 1 electron, and in case of carbon, the 2s has got 2 electrons and the 2p subshell has got 1 electron each. Looking at them and seeing the compounds they are forming, like beryllium forms BeCl2 and a few more compounds, boron BF3, carbon forms a number of compounds, millions of compounds we have in carbon, but here carbon is showing only 2 electrons in its p subshell. Most common example for methane. How exactly the formation of these compounds are taking place, where according to the valence bond theory we are showing that the electrons here is completely filled, here it has 1 electron and here it has only 2 electrons. Here comes into play our hybridization. What exactly is this hybridization? Hybridization means complete intermixing of one or more vacant orbitals. One or more orbitals, intermixing of orbitals which are having either same or slightly similar energies. These orbitals they intermix. How exactly does the intermixing of these orbitals take place? Intermixing means when we consider the next higher orbitals for beryllium, the next subshell is, this is 2s, the next subshell is 2p. If one of the electrons with slight energy from the 2s is promoted to the 2p orbital, this electron comes over here, then we have 2 unpaired electrons in beryllium. These 2 unpaired electrons in beryllium are now ready for hybridization or for bonding with the other elements. Similarly, in case of boron, if the electron from 2s is promoted to the next 2p shell, then we have 3 unpaired electrons in case of boron. Similarly, in case of carbon, which has 1 electron here and 1 electron here, if this electron is promoted over here to the 2pz, this electron comes here and we have 4 unpaired electrons in case of carbon. That means by promoting one of the electrons to the next electron, we are only making the electrons available. Then what is the criteria for hybridization? Just making them available and bonding does not mean hybridization. Making them available and then resulting in the intermixing of these orbitals. In case of beryllium, if this 1s and 1p intermix together completely, we will get an sp hybridization. 1s and 1p is completely mixing, we get sp hybridization. In case of boron, 1s and 2p orbitals, 1s is combining with 2p orbitals px, 2p orbitals, we will get sp2 hybridization. In case of carbon, 1s combines with 3 in this particular case, then in that case we say that the hybridization, if the mixing is taking place between s and all the 3 p's, then it will be s plus p plus p plus p, giving us sp3 hybridization. It is not necessary that all the or electrons or the shells that are available are involved in hybridization. So, what are the necessary criteria or conditions that we require in hybridization? Our first condition is hybridization means the intermixing of the orbitals which are having either same or almost similar energies. This is the first important criteria. The second criteria, how many resultant hybrid orbitals are formed. So, the number of hybridized orbitals formed will always be equal to the number of orbitals that are involved in hybridization. For example, if 1s and 1p is involved in that means 2 orbitals are involved here, we will get 2 sp hybridized orbitals. 1s here, 1s and 1p will give us 2, 1 plus 1, 2 sp hybridized orbitals. If 1s and 2p orbitals intermix together, the resultant will be 3 sp2 hybridized orbitals. 1s and 2p will give us 3 sp2 hybridized orbitals, 2 plus 1, 3. 1s and 3p hybridized orbitals, 3 orbitals mixed together, we get 4 sp3 hybridized orbitals in this case, then we get 4 sp3 hybridized orbitals. So, the second important criteria is the number of hybridized orbitals formed is equal to the number of orbitals that are involved in mixing. Is it necessary that only half filled orbitals are taking part in hybridization? So, let us see the criteria which all types of orbitals can take part in our hybridization. For hybridization, half filled, fully filled as well as vacant or empty orbitals also take part in hybridization. That means not only half filled or fully filled, vacant orbitals can also take part in hybridization. That means all the 3 in any form can take part in our hybridization. We will consider a number of examples where each one of these are involved for our hybridization. How exactly do we represent a hybridized lobe? A hybridized lobe, once it is formed, it is represented as a big lobe as well as a small lobe. This is called a hybrid lobe. After hybridization, we get a hybridized lobe which is represented like this. For example, if we consider simple formation of beryllium fluoride, beryllium has got 2 electrons now. After its 2s electrons, beryllium 1s2, 2s2, the 2s shell, we are not considering 1s, 2s shell has 2 electrons. These 2 electrons, out of these 2, one of the electrons is first shifting, after gaining energy is moving over here. These 2, 1s and 1p orbital of beryllium, they are intermixing together to give us 2 sp hybridized lobes. 2 sp hybridized lobes, and these lobes will orient themselves in such a way that they have minimum electronic repulsion. That means one of the lobe will be oriented like this, the other lobe will be oriented like this. 1 electron here, 1 electron here of beryllium, and with the other it will, if we form BeH2 or BeF2 or Cl2, the other electrons, will form a bond this way, contributing its 1 electron here and 1 electron here, and the bond angle over here will be 180 degrees. Fluorine will contribute from this side and from this side. Each fluorine 1s2 has an atomic number 9, 1s2, 2s2, 2p5 will have one vacant, one electron in this lobe which does not undergo hybridization. So, over here and over here, each of the fluorine, they will form a 180-degree angle and a linear geometry in case of beryllium fluoride. So, this is the first example where we are showing a linear geometry of BeF2. One more important condition for hybridization is only sigma bonds can be used in forming hybridization. Pi bonds are not at all involved. So, if we sum up the important conditions, hybridization means the intermixing of the various orbitals of having almost similar or almost similar energies. The number of hybrid orbitals formed is equal to the number of orbitals that are involved in mixing. Half filled, fully filled and empty or vacant orbitals are also involved in hybridization. Pi bonds are not involved in hybridization, only sigma bonds are involved in hybridization. Our hybridization or after hybridization, the hybridized lobe is represented as a big lobe and a very small lobe at its mark. Let us consider a few more examples of compounds which are showing different types of hybridization. If we consider methane, carbon in methane, carbon having an atomic number 6, 1s2, 2s2, 2p2. Our 2s shell has got 2 electrons, 2p has also got 2 electrons. We are shifting one of these electrons here, 2s2, 2p2, one of these electrons will shift over here and the third electron comes here. As a result, carbon in the excited state becomes having 1s and 3 electrons in the 3p subshells. So, over here as per our requirement, depending on the compound, in case of methane 1s and all the 3 p electrons will be involved because s and all the 3 p subshells, that is 4 orbitals, will be involved in hybridization. So, 1s and 3p will give us 4 sp3 hybridized lobes, 4 sp3 hybridized lobes. How do we show them? These 4 sp3 hybridized lobes will orient themselves forming a tetrahedral structure with the first lobe in this form, the second lobe in this form, the third lobe in this form and the fourth lobe in this form. It is not very necessary to show these smaller lobes. You may show or you may not show. Some of the books are showing them, most of the books are also not showing them. So, these are 4 sp3 hybridized lobes of carbon which have got 4 electrons. Each of these 4 electrons in case of methane will bond with 4 hydrogen atoms. Each hydrogen has got 1 electron in the 1s subshell. We will show them in different orientations. 1, 2, 3, 4, 4 hydrogens. So, each of the 4 electrons can be shown because the electrons of hydrogen are present in the s subshell. It is spherically symmetrical in all directions. So, 1s over here for hydrogen, 1s over here for hydrogen and one more s over here for another hydrogen. The bond angle 109 degrees 28 minutes. A tetrahedral structure forming 4 sp3 hybridized lobes. This is in case of methane, that is showing 4 sp3 hybridized lobes having a tetrahedral structure and a bond angle of 109 degrees 28 minutes. Let us consider some more examples. In case of ethene C2H4, ethene shows sp2 hybridization, has a structure C double bond C, 1 H here, 1 H here, 1 H here and 1 H here. When we look at the structure of ethene, we see that it has got a multiple bond, a double bond between carbon and carbon. It has 1 sigma and 1 pi bond. When we try to see its structure, carbon in the ground state 1s2, 2s2, 2p2 for one carbon, for the other carbon 1s2, 2s2 and 2p2. If the 2s electrons is excited to the 2p shell, this electron comes here and we get carbon in the excited state. This electron moves over here. Similarly, for the other carbon also, this electron comes over here and we have 4 unpaired electrons in case of both the carbon atoms. Now we see that carbon has got 1 sigma bond between the other carbon atom. Between 2 carbon atoms, there is 1 sigma bond. Remaining 4 hydrogen atoms are also showing sigma bond. And here it is observed that in hybridization, because there is a pi bond involved here, only the sigma bonds are involved. So in this case, out of the 4 unpaired electrons, only 1s and 2p orbitals will be involved in our hybridization. In both the cases, only the 3 orbitals will be involved in hybridization, forming 1, 2, 3 sp2 hybridized orbitals. In each case, here also we will get 3 sp2, sp2, sp2. Because the last one is a pi, one of them is a pi bond, one of the carbon and the other carbon links to the other through a pi bond. Pi orbitals are not involved in hybridization, so their lobes will be fully intact. The same picture we can represent it diagrammatically. For example, this is the p lobe of one of the carbon atoms which is not involved in hybridization. The second lobe, one lobe is here. 3 of the lobes are undergoing hybridization. 1, the second lobe and the third lobe. These 3 will form a trigonal planar structure having a bond angle of 120 degrees between them. This carbon will overlap with another carbon atom. This is a complete lobe. This is one lobe. This is the second lobe and this is the third lobe. When we observe carefully, this and this is a complete lobe which does not involve in hybridization. This will form a normal pi bond. 1 electron of one carbon, 2, 3, 1, 2, 3 and 4 here, 1, 2, 3 and 4 here, 1, 2, 3. One hydrogen over here, one hydrogen over here, one hydrogen over here, and 1 hydrogen over here, 1, 2, 3 and 4. These 4 represent our structure CH and CH with a pi, a sigma and remaining all sigma bonds. Similarly, bonding in acetylene, C triple bond C, HH on either side, C2H2, which has got a triple bond, 1 sigma, 2 pi bonds here, 1 sigma and another sigma bond here. Same way, when we split the carbon atoms, carbon in the excited state has got 2s and 2p3 electrons. Another carbon in the excited state has got 2 electrons here, 3 in the p electrons, p shell. When the orbitals intermix as per our requirement, there are 2 pi bonds. That means only 1 sigma bond is present between one carbon and the other carbon. So, one S will combine with another, only one P and form 2 sp hybridized orbitals for each of the carbon atoms. We will have a bond, the remaining 2 will form bonds, one pi bond between carbon and carbon, another pi bond with carbon and one hydrogen will be attached to each of the carbons. A sigma bond here and hydrogen will be attached to each of these, one hydrogen here and one hydrogen here. For example, if we consider the 3 lobes for both the cases, a complete lobe unhybridized, a complete lobe unhybridized for this carbon, a complete lobe, another one unhybridized, another completely unhybridized lobe for this carbon. The hybridized lobe, one here, the other one here, one here and the other one here. So, each carbon has got 4 electrons, 1, 2, 3 and 4, 1, 2, 3 and 4. 1 hydrogen each on either side and thus forming C triple bond C 180 linear geometry is observed in case of these. Because it is sp hybridization, the bond angle is 180 degrees and it is found that because the pi bonds are not involved, the electron pairs of either cases, they are far apart from each other which are undergoing hybridization. We have one pi bond over here and the other pi bond that is formed here. Thus, through hybridization, we have 1 sigma and 2 pi bonds that are observed in case of acetylene. If we consider a few more examples of inorganic molecules, I will be rubbing this. For inorganic molecules like ammonia, NH3. In case of ammonia, nitrogen has got 5 electrons in its valence shell. Over here we have got 3 hydrogens which will be linked. In this case, as we discussed earlier, it is not necessary that only half filled or vacant orbitals are required. Even lone pair of electrons or fully filled can participate in hybridization. Ammonia, because it has got a lone pair of electrons, it shows sp3 hybridization as it forms with 1 hydrogen here, one hydrogen here and one hydrogen over here, a final structure, a pyramidal structure H, H and H and a lone pair here. So, seeing these examples, we can also say that by calculating the steric numbers of each of the bonds that are present or the lone pair of electrons that are present, we can also indirectly calculate the hybridization of the compound if we cannot, or every time we cannot represent the structure of the molecule. In that case, for example, a single bond has got one steric number, a double bond also contributes a steric number, triple bond also contributes to only one steric number, and a lone pair of electrons also contributes to one steric number. That means in this case a sigma, 1 sigma, 1 sigma are contributing. So, the total steric number of this particular molecule 1 plus 1 plus 1 plus 1, that is equal to 4. The steric number in this case is equal to 4 and this represents sp3 hybridization. 3 plus 1, that is equal to 4. So, the hybridization in case of ammonia molecule is sp3 hybridization. Similarly, instead of writing the structure for water, complete showing the hybridization for water, looking at the molecule of water, water molecule H2O. When we write the electron dot structure of the central atom oxygen, 1, 2, 3, 4, 5 and 6, one hydrogen here, one hydrogen here, it has got two lone pairs, each hydrogen contributing 1 electron pair, one sigma bond here, one sigma bond here, two lone pairs. The steric numbers will be 1 plus 1 plus 1 lone pair plus another lone pair equals to 4. So, steric number is equal to 4. So, the hybridization again in case of water is sp3. Though the geometry is not tetrahedral, depending on the number of lone pairs, there is a distortion in the geometry, but hybridization in case of water is also sp3. In case of ammonia also it is sp3. We can calculate the hybridization of many compounds or the ions by using another formula which we require for competitive examinations. We can use the formula hybridization H is equal to half the number of valence electrons plus the number of monovalent atoms attached minus the number of cations plus the number of anions present on that compound or substance, whichever is given to us or the species. For example, if we have NH3, the same formula we will apply over here. In case of ammonia, we have calculated the hybridization of ammonia through the steric numbers also. Now, through this formula also we can calculate hydrogen H hybridization will be equal to half into number of valence electrons will be 5 plus number of monovalent atoms. Number of monovalent atoms, hydrogen is a monovalent atom, it will be 3. There are no cations or anions attached here, that is 0. So, total will be 8 divided by 2, that is equal to 4. So, the hybridization will again be equal to 4, that is sp3. Similarly, for water, using the same formula, H is equal to, in case of water, H is equal to half number of valence electrons on the central atom is 6 plus 2 monovalent atoms attached to it is 2, no ions attached to it is 8 by 2 is equal to 4. Water also shows sp3 hybridization. Now, these are neutral molecules. Let us apply the same formula to some cations or anions. In case of carbonate ion, If we consider CO3 2 minus, it is observed that hybridization H will be equal to half into number of valence electrons of carbon is 4 plus 2 ions of the anions. As there are no monovalent atoms here, we get 6 by 2 is 3, thus showing carbonate ion as sp2 hybridization. Similarly, we can calculate the hybridization for PCl5. PCl5, the central atom, hybridization H is equal to half into 5 plus 5, because there are 5 monovalent atoms, divided 10 by 2 is equal to 5. Hybridization in PCl5 is sp3d, as it shows sp3d hybridization, as it has 5 orbitals involved over here. So, thus we conclude by saying that hybridization is intermixing of the atomic orbitals of having similar or almost similar energies between s, p and also the d orbitals. So, on mixing we can get different types of hybridization. The different types of hybridization can be listed as sp, sp2, sp3, sp3d, sp3d2 or d2sp3, the most common of all these hybridization. I hope you all have understood. In the next class we can work out a few more examples on these. Thank you.